Good evening. Welcome to the second lecture on the neural networks and what do we do with that different networks. So today I want to make a lecture on different neural networks architectures and basically the ideas that underlie these different architectures that we have. So let me recap just a little bit what we previously had. So we have already considered the idea of having a single neuron that should mimic some neurons from the real world. This neuron gets some inputs from the outside. Inside of this neuron we are performing, so it's some sort of performing operation. If I have inputs A1, A2, I don't know, AN, I am summing all AIs times WI inside this neuron with respect to I may add some bias and I use some activation function f on this. And this result, I have some sort of output of this neuron, and this neuron outputs me a value. So activation functions, we remember, they may be different. Most cases we use something like ReLU. We know that we can take a bunch of neurons, collect them together and make a neural networks layer. Here is a layer. So here we have different neurons. They are sending some outputs from the layer and they are getting some inputs in these layers. Few neurons can get input from one source. So here I'm showing that like this node, and I have few neurons getting input from this node. There may be some different node here. Few more neurons are making connections to that node, and so on. Depending on the type of this layer, we may have different arrangement of the neurons and different operation that they perform. We mostly considered a so-called convolutional operation, but of course we have seen a fully connected layer or linear layer in terms of PyTorch and like average pooling layer, max pooling layer, so on and so forth. And now the time came to take different layers and connect them into one architecture. So we will take a separate layer and say this is a convolutional layer, some different layer, call it average pooling layer, and connect them and say that information goes through these layers, goes, and then we get some sort of output. The way we connect these layers and what exactly layers are we using basically defines what we call a neural networks architecture. And today we will consider a few different architectures and different ideas that underlie these architectures. So starting from the simplest one and going further to more and more complicated ones. Okay, so probably the simplest architecture you can ever imagine is something like LeNet. So here is LeNet. It was first developed in 1998 by Yann LeCun, so that's why LeNet. And this is probably one of the first successful convolutional neural networks applied to handwritten digit recognition. And you probably heard about dataset called MNIST. This is a dataset of different handwritten digits, and basically this neural network paved the way for modern deep learning in computer vision. So that was the first case. It used hyperbolic tangent as an activation. At that point ReLU was not yet popular, so in the modern networks you probably will not find that hyperbolic tangents, or at least very few of them, and mostly you will find something like ReLU or some leaky ReLU, something like that. But that network used hyperbolic tangent. It used average pooling. Well, modern neural networks are using more something like max pooling, Pretty similar operations. When you get your image from the input, you just split it into parts. So here you have some sort of image from the input. You split it into some parts, like this one. So I'm taking parts like 2 by 2, and I'm calculating, in case of average pooling, I'm calculating an average. In case of max pooling, I'm calculating some max value. So here I set a max value out of these four numbers, and in here I will set max value from these 4 numbers, and so on and so forth. So you get the idea. And there were no layers like dropout or batch norm, because these techniques were at that point non-existent. So that's why LeNet 5 is much swallower and simpler. The idea of the LeNet, the underlying idea, was basically using alternating convolutional and pooling layers. And you will see this idea in modern networks as well. So you will see like many networks where you use convolution, then you use at some point you use some pooling technique. The idea of convolutional layer, that was a breakthrough, I guess, because they came to this idea through so-called weight sharing, when they thought about each new generated pixel as generated with a separate neuron. But they said, okay, all these neurons should share weights and use basically one and the same kernel to generate that new pixels. That was really good because of the reason I have already told you, that convolution considers some sort of geometry of the pixels. So if you have some neighboring pixels, they are convoluted together, and the result you get, in some sense, it takes into account that these pixels may represent the same object because they are in the vicinity of each other. The number of parameters was just something like 60k, so that's really tiny by modern standards. And bias variance balance is a good example of a simple model that avoids overfitting by design. So you should not be concerned with overfitting with LeNet. Well, convolutional neural networks are, I guess, pretty stable with respect to overfitting, and in most cases you get some decent results without any overfit. So I would say that. Here is example of that architecture. Here you see in yellow shown convolutional layers, red these are max pooling layers. You see the different number of channels you have in the output, so depending on the layer. So here you see these numbers like 6, 16, so on and so forth. These are the number of channels. That means that if you have some inputs, a number of input channels, you convolve everything you have there, you weight, you multiply that by certain weights, you add that, and you put that into the output. You do that some number of times, you get a number of different output channels. So maybe, I'm not sure if I should show this, but let's do that. So if you have some number of input channels, so here is, so these all are some sort of images. So we have some pixels in here. They may come from some different layers, so they may be generated with the previous layer. They may be reshaped from some data, so whatever. So these are then you have a kernel. You have a kernel like 3 by 3. Each of them is convolved with this kernel, So you have seen the picture how the convolution is performed. You basically place this kernel, you step with the kernel along the image, you probe all these pixels, you multiply coefficients in the kernel by the values in here, add them together, you get the final result. This final result gives you a picture. So here you have results of the convolutions. Then you add them together, multiplied by some additional coefficients. I know, call them omega 1, omega 2, and omega 3, and you get your final output. And if you do that few more times, like take this block, and that is one output channel, and do few such blocks. So like you have one block here and you have the same block here, you use this information in here, you get one more output. This will be second output channel, and so on. You can make as much as you want, so as many as you wish. You can make 10, 20, 100 channels, whatever. So that's basically what you see here. So these numbers, they define the number of channels that we have here, and thus we use convolutions with different number of input and output channels. So I will not go into very details for every architecture, but just this one is pretty simple, so just look at it one moment. So here we have it implemented with the PyTorch. Once again, you can check the files and see this code. Here you see layers that I create these layers in the constructor: convolution, average pooling, convolution, average pooling, convolution, and two fully connected layers. And here you see the function forward implemented, and this function basically performs convolution, then hyperbolic tangent as the activation function, then pooling, convolution, hyperbolic tangent, so on and so forth. At the end you see the fully connected layers that generate the result. I'm not sure if I need to do that, but okay, let me start. Once again, creation of the model and training. Here you see preparation of the data. So we have data MNIST. These are images with the numbers and some sort of ground truths, so that we can train our network and we can test how good it works. Here you see the training process. Once again, I use cross entropy loss as the loss function that defines me how good is my model performing. I use ADAM optimizer, pretty good optimizer, so I use it almost everywhere, but remember that there are many different, so you have from what to choose. And here you see the training process is underway. Our loss started from 287, and now after 3 epochs it's 59, 45, and at the moment we will get the final result. And here I start the evaluation process. So here we have found our loss, and here the result of the evaluation tells us that we have a very nice accuracy. So most cases we get the correct digit based on the image of that digit. So we have considered the simplest network, LeNet. Let's move to the next network, AlexNet. That was developed by a PhD grad student, Alex Kryzhevsky. That's why AlexNet. He's of Ukrainian descent, so that's a neat point to notice. And he worked in collaboration with Ilya Sutskever and a Nobel laureate in physics, Geoffrey Hinton. So Geoffrey Hinton got his Nobel Prize just recently, I guess 2024, At that point he wasn't Nobel laureate, but anyway, you guess that these people definitely understood what they were doing, and they really created a breakthrough. So AlexNet won the ImageNet large-scale visual recognition challenge in 2012 by a huge margin. So that was a really breakthrough, and that was probably the first really deep network. So at the moment I'm not sure if anyone uses these exactly networks, so it probably has now more like historical reasons to consider, but anyway, there were many interesting ideas implemented in this network that are really worth mentioning, and that you will see in the modern neural networks used here and there. So it's not only was a catalyst for deep learning, but introduced a number of different ideas. So what were the new ideas? First, the deep architecture. So before this moment, mostly people tried to create some shallow networks. This one was really the deep one. It introduced the ReLU activation instead of hyperbolic tangent, and you will see this ReLU activation everywhere in, I guess, in all the modern neural networks. So wherever you look, you will probably see some sort of ReLU. You probably see that we have a little bit dimmer light. That's because we have power outages in Ukraine, so that's the best what we were able to do. Okay, so let's continue with new features and ideas that were introduced in AlexNet. So that was, I guess, the first neural network that introduced deep architecture. Probably all modern networks are deep neural networks, but that was, I guess, the first one. That was this network introduced, or at least really popularized, a usage of the ReLU activation function instead of hyperbolic tangent and sigmoid function for faster convergence. And probably all modern neural networks, you will find ReLU functions there. This neural network introduced dropout. So I have already mentioned this sort of layer, the dropout. That's when you are training some layer, you have neurons in that layer, and you can turn that neurons on and off during the training to force them all to train and to contain the information that you need for the successful work of the neural network. So if you have some neurons, so I have, let's be simple. So suppose I have two neurons, they get some inputs, they generate some outputs, and these outputs go somewhere else. So here is some next layer, this was some previous layer, and these are two neurons. And it may happen that if you train that, one neuron will perform its work pretty decently, while the other one will slack off. So what you do, you can turn one of them off, you can train this network and thus force the other neuron to perform some useful work. Then you turn this back on and you turn off this one, you train the network, once again you force this one to do something useful. And at the end of the day, when you have trained everything, you can turn them all on, and you will get a bunch of neurons that all are inclined towards performing something useful, not just returning some sort of zeros or something like that. So that was really good idea, and that prevented overfitting. It used overlapping 3x3 pooling with Stri2 instead of 2x2 non-overlapping. Pretty interesting idea, pretty decent idea, used still up to this day. It used data augmentation techniques to increase the size of the dataset. So we know there is a problem of overfitting, when your neural network is basically just remembering whatever you have in your train set. So it's a problem because if it just remembers your train set, it will not properly generalize your data and perform, it will poorly perform on the examples it had not seen. So this problem often arises if your data set is too small. So you have a small data set, it's much easier to remember the data set than to generalize and to find some general features and somehow correctly process whatever you have in your data set. So it may be quite complicated to create a large data set in many cases, and they were probably one of the first who came up with the idea. So we have small data set, let's somehow change the data set, let's augment it and make a larger data set that can be used for training and thus avoid somehow the problem of small data sets. You can see that today as well there are certain libraries, let's say library Albumentations for example, that gives you the ability to augment your data sets. If that's data set with images, you can probably somehow rotate that images or shift them, some translation, perform some translations, scaling, so on and so forth. And if you have some ground truths, you can do the same operation on your ground truth. That may be some sort of mask, for example, for that image, if that's the problem of semantic segmentation, for example. And thus you can increase the size of your data set from from small size to some, let's say, to moderate size, or from moderate size to some large data set. So that's really good. One of the ideas was training on two GPUs, splitting the model across them, so model parallelism, and this idea still can be used today by neural networks, by very large neural networks. And it used local response normalization to encourage lateral inhibition. Now less common technique, I'm not even sure how that works, being honest. So here you see the architecture of the AlexNet. Once again, yellow are convolutional layers, max poolings are these red things, and here you see in green and violet you see some sort of fully connected layers. Pretty reasonably resembles LeNet, but it's much deeper and employs all these techniques I mentioned to make it work. I will not start this code, and here is just an example of that architecture. You see that once more, but printed with sort of PyTorch tools. So here you see different layers like convolution, ReLU, max pooling, so on and so forth. So you can check that if you wish later. VGG16, so Visual Geometry Group Network. The thing is that when developing these neural networks, there are many different methods. You can make them deeper and deeper. Probably one of the, let's say, philosophically simplest is the method of just increasing the number of layers and looking what can we get out of it. And it turns out that if we are increasing the number of convolutional layer, we can get pretty decent pretty decent size of the neural network. So here is the example, VGG16. I guess in all with these networks we can get up to 19 layers, but that's including fully connected layers. If you do that increase further, we will get certain problems. They're like too small gradients, it stops training well, so we have some problems that were typical for deep neural networks at that time, but anyway, still interesting and still can be used to extract some features in modern neural networks as some sort of first stage to get some interesting features from the images. Okay, so what kind of idea do we have here? So this is a deep convolutional network for image classification. The key idea was to use many small 3x3 convolutions stacked deeply instead of fewer large filters. So before, people tried to use some large filters, 5 by 5, 7 by 7, 11 by 11, and even more. And it turned out that 3 by 3 is good enough. You can do many things with them and they will work pretty decently. These are just different convolutions, so you have stacks of 3 by 3 conv layers. Every few convolutions you get a max pool. The idea we have already met. These max pool, they have spatial resolution. Regarding depth, I have already told you, and the classifier uses fully connected for 1000 ImageNet classes. Why it works? Well, small filters give deeper, more expressive network with manageable parameter count, and this uniform architecture like convolution pooling is pretty simple and interesting design. So that's a strong baseline model for feature extraction and transfer learning. So if you need to create some neural network, you can use as the first stage VGG to extract certain features, and then you can work with that features pretty okay. It can be applied to image classification. It's used as a backbone in vision tests, say before ResNet, and it is still popular as a feature extractor, as I already told you. Architecture FCN32, that's fully convolutional network for segmentation. Here you see once again the image. You already should recognize convolutions and max pools. So here they are. That was the first major CNN adapted for semantic segmentation. What is semantic segmentation? That's basically when you get an image and you produce as a result a new image where each pixel is classified. So you tell that this pixel belongs, for example, to a car, that pixel belongs to a tree, so on and so forth. So you get some bunch of masks, and then each of these masks tells you whether this pixel belongs to the object of certain class or it does not. So that's basically depends. So the key idea was replace fully connected layer with some sort of convolutions that allow per pixel classification. So here you see in the VGG16 you see these fully connected layers at the end. So these magenta bars, these are fully connected. In this architecture in FCN you see no such bars, so just convolutions. So architecture, so a backbone often uses pre-trained classification nets like VGG16 as encoder. So you can use part of one neural network as the first or some subsequent parts of another neural network. So you can take neural network, you can train it, then you can take part of it, insert it into another network and use it, and basically freeze that weights and train only the rest of the network. So that's pretty okay, you can do that. So fully connected layers were replaced by one convolutions. And here we see the operation of upsampling. We often hear the term deconvolution. So that's basically convolution, but that makes our image larger. Feature maps were upsampled by a factor of 32, so we get to original image resolution. And they can produce coarse segmentation masks. So you see that here at the end we have some sort of deconvolution. So that's like some convolutional layer, but that makes your image larger. And you can find that, of course, in the PyTorch. And that is used to make larger output image that corresponds to the by the size to the input image. There are certain variants like FCN16.8 that improve localization by fusing encoder feature from shallower layers, but we don't get into that. So why it works, that basically converts classification network into segmentation networks. So that is end-to-end trainable, so you have input image, you have output segmentation mask, and you can compare that mask to some sort of ground truth. The first step, that was the first step towards modern encoder-decoder designs. We will look into that. I will show you U-Net, I will show you some different designs. It can be applied to general semantic segmentation, and that's a proof of concept that convolutional neural network can do dense prediction, not just classification. So the architectures before were more targeted towards classification, and here we see some sort of semantic segmentation that is more, let's say, interesting, and that paved the way for different architectures like U-Net and so on. We'll get to that. Architecture ResNet. Res comes from residual, so residual network. This contains one more pretty non-trivial idea. The thing is that when training a deep neural network, we have a problem with the gradient. This gradient gets smaller and smaller when we are backpropagating through the neural network. So we have already seen the process of the backpropagation, and you know that during this backpropagation we are sending that numbers from the layers backwards from the output layers to the input layers, and we are constantly something multiplying, so on and so forth. And during this multiplication, it turns out that the numbers will get smaller, smaller, and smaller while we get to almost zero, and some initial layers, they are just not training. So that was some sort of cap that prevented us from making neural networks even deeper. Despite we knew that it's good to make it deeper, we probably can get some better result with a deeper neural network, but we just can't train it because we have this sort of problem. And here is the key idea. Why don't we create some sort of residual connections so that we allow this gradient to propagate not only through the layers like in here, so here is our output, and from the output we can propagate gradient through the layers, but we can propagate that around the layers, and in this way we can avoid getting that gradient to zero. And this idea was pretty decent as it turned out to be, and the first, I guess, architecture that presented this idea was ResNet, and I guess they are used up to today. So the key idea, so residual connections or skip connections, they allow layers to learn only the difference residual from identity mapping. So here you see these plus signs, they show you that we have our initial data that was taken from here, and this data gets here, and you add some epsilon from these layers. So it learns only the difference. Well, and the second important thing, that gradient will propagate backwards through these skip connections. So building block of this layer is so-called residual block. Nothing fancy, just input, some convolutions, and then output. So convolutional layer, but inside of the block you just get some trivial convolutional neural network. Types of residual blocks. So basic block used in ResNet 18 and 34, it has two 3x3 convolution plus skip connection. You may have so-called bottleneck block used in deeper ResNets. That's 1x1 convolution to reduce dimensions, then 3x3 convolution, then once again 1x1 convolution to restore dimensions, plus skip connection. Well, if input-output dimensions differ, shortcut uses 1x1 convolution to match shapes. That may happen, so you are skipping all the layers inside that with your residual connection, and of course you need somehow to match the output dimensions to make it all working. So why do these residual connections help? So deep plane networks suffer from vanishing gradients and degradation problems. So that's what I told you, that gradient is getting closer and closer to zero when you are backpropagating that. Skip connections let gradients to flow directly through identity paths, so it just avoids getting through all that layers, and that's really good because it doesn't diminish, it doesn't get closer to zero, and model can easily learn identity mapping if deeper layers are unnecessary. So that may prevent you from making your neural network too deep. So you create many blocks, but if some of these blocks are not needed, that's not a problem for the neural network. It just will skip them, and that's it. It can be applied in image classification. So for example, that was ImageNet benchmark winner in 2015, used as backbone for many CV architectures for object detection, like faster RCNN segmentation, mask RCNN, UNet variants, so on, and adapted to NLP, speech, and other domains where these kind of models are useful. Here is example of creating that ResNet. I will not get into all of the details. We don't need that. What I want you to show, probably, how do I find this? Here you see the basic block used in the ResNet. You can do a separate block and that use it in the another neural network. Here you see in ResNet small these basic blocks are used. And what's interesting in this block, that we have certain convolutions. Here you see I'm creating convolutions, I'm adding some batch normalization, like in previous ideas, but what's interesting, I am adding some shortcut. So here is a shortcut between the input and output, and here you see in the forward function I am getting my data, this x, through convolution, ReLU, convolution, batch normalization, so on and so forth. But at the end I have this sort of shortcut. I use this shortcut and I add it to the output. and that's how this neural network is made. So here you see the architecture in its full glory. So some initial layers, then we have our basic block in here. So this is our basic block, and here we have some sort of skip connection. So I even made it a little bit more complicated by adding just few layers in here. So if we we can make a pure skip connection just by threading information from here to here, but we can add one or two convolutions just to do something during this skip connection. Here you can see this architecture goes on and on. So now they are collected together. Here is another block, another skip connection. Once again they are collected together, block, skip connection, so on and so forth, and here we get the output. So that's it. I will not get through all these training operation and so on. I guess you believe me that it can be trained and you get some decent result. Autoencoder, one more neural network, so one more architecture, and this one is pretty interesting because that it introduces some more new ideas. Before we get into that new ideas, let's consider the problem a little bit more accurately. In some cases, you may want to make from a high dimensional data some lower dimensional data, and there are many methods to do that, some of them in classical machine learning and some of them with neural networks. Basically, autoencoder is a method to transform from some higher dimensional space into a lower dimensional space. Your higher dimensional space may be almost anything. In case of autoencoders, it's often the space of all possible images. So you have some sort of image, it has 100, no, 100 is too little, let's say it's image 100 times 100, so that's 10,000 pixels. So you have a space of 10,000 coordinates, and you take a point in that space. That point corresponds to certain image, 100 times 100, and you want to get into some smaller space that contains, I don't know, 1 coordinate, 10 coordinates, so something like that. Maybe some larger, 100 coordinates, but you get the idea. And this is the place where autoencoder may help you. I want to show you first, before that, just a small demo how that's performed in the case of lower dimensional spaces, like if I want to get from 2 dimensions to 1 dimension. And why may I want to do that? So suppose I have measured something, and here are the points I have measured. So here they are. These points are certainly living in a 2-dimensional space. So each of these points is described with 2 numbers. But if you look carefully, you see that these points are pretty close to certain line. And here I'm trying, and if I make that line a new coordinate line, I can probably remove the other number and still get them pretty accurately described. So here I am changing my coordinate system. So here I have coordinate system. I move this coordinate system. Here you see projection of the points on different coordinate lines. And if I rotate this coordinate system appropriately, it turns out that I can find that sweet spot where one coordinate has projections almost equal to 0, while the other one has them spread out. So that may be the case that I want to have. So now I can remove one of the numbers and describe my points with just one number. And this is good because many methods of machine learning, they don't like too high dimensions, especially if it gets to classical machine learning or something like that. So you may want to compress your data into a lower dimension. But this is the case just with 2 coordinates and the output with 1 coordinate. What should we do if we have images? With images, image 100 by 100, that's already 10,000 coordinates. So what do we do with that? And here we have our architecture autoencoder. You see the architecture contains of 2 parts, so part of encoder and part of decoder. And here is and you see that sizes of the outputs of the layers of the images generated by that layers, they shrink. So when we get to the end of the encoder, we have some much smaller image than the one we began with. So we have somehow compressed our information. But of course, just compression does nothing. So how do we check that this compressed information is really meaningful? Because I can make small image but just put there some random numbers, so that won't give me anything. So why is that good? I should be able to recover from that compressed image the original image. So only in this case that will mean that these numbers in that smaller representation, in that smaller space, are meaningful. They contain the information I had in the initial image. And here you see the decoder is basically performing that task. It takes that small image, compressed image, and tries to decompress that and to get the initial image. So we can compare what we had at the beginning and what we have at the end. And if they coincide, this means that this information bottleneck really contains all the information we had in the initial image. So that's a pretty interesting idea. So in that will help us to make our our images, to compress them into something smaller, and to use that smaller representation, well, to do something in the subsequent steps. I guess we'll get to some examples. So what do we have? So autoencoder contains 2 parts. Encoder maps input into the so-called latent space. Decoder reconstructs from latent space into the initial space. Architecture often has symmetric structure, so encoder and decoder just mirror each other. Some common layers we use most often convolutional layers, maybe fully connected, may be used in some cases, but whatever, I have seen mostly fully connected, maybe some average poolings. And the bottleneck layer, it basically represents the compressed features. Where do we apply this sort? Dimensionality reduction. So we have just compared that to the PCA method. So whatever I showed you, that demo, this is basically PCA. So that's dimensionality reduction. We can use that for denoising, so that removes noise from corrupted input. You may train this thing on some data, you can train it to reconstruct images, but the thing is, when you are putting information through that bottleneck, you may expect that only essential information is getting through. So if you have some noise in your initial image, it will not be able to get through that bottleneck, and you will lose that noise and retain only the essential information. Thus, the coder will reconstruct the denoised image. You can use that for anomaly detection. If you have trained that on something and then you get some different image, you will get poor reconstruction, and you can detect that, oh, my autoencoder has poorly reconstructed whatever I have here, so probably it's some sort of anomaly. And of course, image compression and synthesis. So denoising autoencoders, once again, you train with noisy input and clean target. So you have some input, you add some noise, you put that into the autoencoder, then the output you demand to coincide with the clean data before you have added any noise. And they may help you, of course, extract some robust features from your images independent on the on the noise. Here is example of the autoencoder architecture, so not getting into there. So you see I have encoder part, here is convolution size 16, here is ReLU convolution size 4. So here you see the sizes. Here we have decoder. Once again, this is a deconvolution, so that's convolution that makes our image bigger. You do that with the stride, and I will not get into details, but you can check the PyTorch documentation for different layers and get a bit more details there. Just think of it as a convolution that can make your data, make your image larger. And here we see once again ReLU, convolution transposed, and sigmoid. And here I apply these to the input, and I can get some denoised image. Here you see this architecture drawn with the methods of PyTorch, so just different sizes. So output I have image 28 by 28, the output is 14 by 14, it gets through ReLU, then 14 by 14 is squeezed more to 7 by 7, and this is basically the bottleneck. Then we get through this bottleneck and we start increasing the size of the image from 7 by 7 to 14 by 14, from 14 by 14 to 28 by 28, and we have returned to the original size. Here is example of training that network. I will not stop on it, I will just show you the final result. Here we have some noisy data. We put this data through the autoencoder that was trained on the MNIST, and here we have some denoised data, and on the bottom you see the original data. Of course, there are certain differences between denoised data and original data, but we clearly see that it looks much better than the noisy data we have started with. So that's what we have. One more architecture, variational autoencoder. So we have already considered the autoencoder, and we know that autoencoder can take some input data, as we see here. So here is some training data. It encodes it, transforming into some sort of latent space, so space of a lower dimension, and then it can decode it, reconstructing back what we had. The problem with conventional autoencoder is that that latent space is in some sense a little bit meaningless. So we are compressing our data to get a point in that space, but we are not sure if that points have any connection between them. So if they are more or less can be more or less meaningfully interpreted. For example, I have images of squares, of different squares, and I have some sort of latent space, and I want the points in that latent space corresponding to squares to be somewhere near one each other. But we have no such warranties in the case of conventional autoencoder. So here is the idea. Can we force somehow our neural network to make this situation better? So here is on the left is example of the irregular latent space that is generated by the conventional autoencoder. So here we see different pictures that were mapped into this space. So here we see a circle, a triangle, a square, and so on. And here you see points corresponding to them. And here between these points are many points that do not correspond to any meaningful geometric shapes. Here on the right, on the other hand, is a regular latent space. This space is much better because the points in this space they have certain meaning. What do I mean by that? Please consider we have once again a circle, we have a triangle, we have a square. But if we take a point somewhere in between of them, we get something that looks like a little bit of triangle and a little bit of a circle, or a little bit of a square and a little bit of a triangle. So these points, if I will move in the vicinity of my mapped figures into this space, I will probably get something similar to them. But not something that is absolutely off and has no geometric meaning. So let me draw maybe a little bit here. So suppose I have a very simple latent space in form of one dimension. And I have images of, let's say, a circle and a triangle. So that's the only thing I have. But of course my circles may be different sizes, they may be a little bit deformed, so let it be. Triangles may be a little bit irregular, so something may happen. And in the case of conventional autoencoder, they are mapped all over the place. So I can have this circle mapped here, while this triangle mapped here, then this circle mapped somewhere here, and this point, if I reconstruct it, I get, I don't know, something like this. So that looks pretty irregular, and that is not what we want. What do I want to get with the variational autoencoder? I want to get a pretty different picture, let's say like this one. So I'll draw you in a minute. So here I have these circles. So I want these circles to be mapped into sort of one cluster. So here I have different circles, they are mapped here. Here I have different triangles, they are mapped somewhere here. And if I have some point in between circles or triangles and I reconstruct it, I should be able to get maybe something like this. So something in between a triangle and a circle. So maybe not a fully triangle, not a fully circle, so something in between. And that is much more interesting and much more useful in practice, because now your latent space has obtained certain meaning. And you can use it somewhere in some different scenarios. Here is example almost like the one I have shown you, but in case of 2D latent space. So here we have different triangles, rectangles, and circles mapped into the plane. If we move somewhere in the vicinity of these points, we get some sort of triangles, rectangles, and so on. If we get somewhere outside, we get something meaningless. But in case of a regularization, we have this sort of picture where they are a little bit overlapping, and if you get something from the overlap, you see that this thing looks like something in between circle and triangle and rectangle, so it's something much more meaningful. Here is one more example of that regularization. When I am moving from the point that represents the triangle to some different points, and here we see how this shape changes, and it is basically morphing into the circle. Here you see the circle morphing into the rectangle and into the square, and this square is transformed into a triangle. So here is sort of regular space, and that's the goal that we want to reach. How do we do that? Now, instead of just leaving the choice of what is the meaning of the latent space to the neural network itself, so just whatever it generates, everything is good, yeah? Now we change that. So we say, okay, now we want to interpret whatever the neural network generates as something. That something are parameters of the distribution. Okay, so what is this distribution? Consider this picture once more. Here you see the point where the triangle mapped, and here you see some sort of points around. So I can claim that I have some some probability distribution that tells me what is the probability to get a triangle if I sample one of these points. I can treat this probability distribution as a normal distribution. So it will have some mean value, some variance, so on. So I have some mean and variance for that distribution. And of course, these are some other distribution for squares, for circles, and so on. So now I demand my neural network not just squeeze the image, but generate me numbers that I will interpret as parameters of a normal distribution. And this normal distribution basically will be used to generate the image with the decoder. Here, let me first show you the architecture, and I will explain you in a bit why do we need some different things. So here we have an input. This input goes into the encoder. Now encoder generates mean values and variances for a number of normal distributions. I define that number by my own, and here they are. Then I use these numbers and some sort of random number generated with normal distribution with mean 0 and variance 1 to get some random point. So here it is. I use this random point in latent space to reproduce whatever I had at the input. So that's pretty interesting. Here we have some loss function. I will not get into the details, why do you write it this way and so on. The only thing I mentioned that here we have some sort of trick with reparameterization, just because if we use straightforwardly normal distribution with the given mean value and variance, we will get into troubles because we don't know how to propagate gradient through the random function. So if we generate a random variable, we have some note. You can have a neuron that generates you a random variable, but you cannot propagate gradient through that neuron because you don't know how to calculate that gradient. So that's it. It may not have some training parameters. and that's why we will in some troubles here. But it turns out that you can rescale this normal distribution, so you can have neuron that gives you some random number with the normal distribution that has mean 0 and variance 1, and then having this mu and sigma, you can just perform certain mathematical operations and rescale that to get random number that looks like generated with normal distribution with these parameters mu and sigma. So that's it, and that's why you have this sort of architecture. So you have these neuron generating you some random data, but it is not trained, it's just hard-coded, and here you have your gradient propagating back to the encoder, because that encoder defines you mu and sigma. Okay, so so with that being said, so here is once again example of the variation autoencoder. Here you see the reparameterize function that performs that reparameterization. Instead of variance, I use logarithm of variance, but I'm not sure if that really matters so much. And here you see forward, so I call encoder, I get mu and logarithm of variance, I perform reparameterization to get z, and z goes into the decoder. So here you see that, here you see the architecture. Here we have some input, here we have these outputs, and here you see how everything is basically generated. So so nothing really fancy, you can check that. Here is some sort of training, I'm not getting into the details, it just learns to reconstruct numbers from MNIST. So probably we need some better demo, but that's what we have at the moment. One more architecture, U-Net. So we have already seen the autoencoder and variational autoencoder. That's good. Let's remember the autoencoder and augment it with one new idea. So we use skip connections as in ResNet, and this sort of architecture with shrinking layers and then making them bigger as in autoencoder, and look what happens. We get new architecture called U-Net. So probably by this sort of image you can guess why it is called U-Net, because it resembles letter U. This architecture is designed for image segmentation, especially in biomedical imaging. You can guess that shrinking layers, by shrinking these layers, you can, and making these skip connections, you help it consider features at different scales. So you may have some object, a photo of some object, but you can make that photo closer or further from that object, and you definitely need somehow to some mechanism to consider different scales of that object, and that is performed with this sort of architecture of U-Net. So in the architecture you have once again some path, some contracting path, the encoder. Each step halves the spatial resolution and doubles the feature channel. So you are trying to retain information, but you are considering different sizes, and it helps you to capture the context. And you have decoder or expanding path. You are doing some up convolutions, so or so-called transposed convolutions. We have already seen. So each step, of course, doubles the convolutions, but halves the feature channels. And at the end, it restores the spatial details. And we have skip connections that feature maps from encoder are concatenated with corresponding decoder layer, and they are and with these skip connections we are trying to preserve fine-grained spatial information. So in the case of variational autoencoder, that fine-grained information, it was lost. So whatever we had some small features on the initial layers, we did not have them at the end, because you should pass these through all these layers where you shrink everything, and you probably lose that information. But here you concatenate your initial layers to the final layers, so if you have some small features, they are retained, and then they can be used by your neural network to calculate something useful for you. Why it works? Well, because encoders extract hierarchical features, some shapes, textures, semantics, and decoders alone that will be blurry if you don't have that skip connections. Now they can use information from skip connections from higher resolution layers and get you some better result. And that allows you precise pixel level predictions with relatively few training images. Where do you apply that? Biomedical imaging, maybe satellite, aerial imaging, general semantic segmentation, or variants adapted for 3D volumes. Here is an example of that UNet. I'm not going into the details, just show you the image of the architecture. Here we have some convolutions and ReLU. Here MaxPool makes layers smaller, and here you see skip connection went down. So here is the skip connection, is going down, down, down. Once again, we make everything smaller, create one new skip connection. Here we concatenate what we had, some small image with that skip connection. We upscale everything. Everything goes up, concatenated with the initial features, and processed through some convolutional layers once more. And here we have some result. As an example, I will show you some segmentation. Here we have a data set from Oxford, pet data set. There are different breeds of cats and dogs in the data set, but since I thought that we will run this network online, I have pretty decently shrinked the size of the data set by leaving, I guess, just 2 breeds of cats. But since we have power outage, I'm not able to run even that, so probably we will just look at my previous results. So here are results of the training. Here you see the image. Here you see our ground truth. That's a mask. Ground truth for these data sets looks like some pixels are ones. They tell you that that is definitely pixel of a cat. Some are gray, so they contain values something like 0.5, and they define you some sort of boundary of a cat, if I can say so. And here you see the prediction that we have after our neural network. So you see that if we train a UNet, we can get some sort of well, more or less correct predictions. Of course, I used a really small UNet, and I trained it just for, I don't know how many of them epochs, just for 100 epochs, so that's almost nothing. But you see that we already have some more or less decent result, and it is able to segment cats. And if you have some picture of a cat and you want to remove the background, for example, to have only the picture of a cat, or to change that background to something, you can already use this sort of neural network. One more architecture, generative adversarial network. These networks were very popular a few years ago in the context of the style transfer. So here is an example of that style transfer, just to remind you in case you missed all that hype we had. So here is some sort of random photo. That's photo of some random cat, and here you see an image. This is a picture of condensing, and I can train this neural network, and it can make me a new picture, a cat that is drawn in style of Kandinsky. So looks pretty interesting, and we all loved that sort of neural networks, but I guess they have lost their popularity at the moment. So what is that generative neural network, and what kind of ideas does it contain? This is a pretty interesting network, and it looks as follows. So I generate some random input, and I put it into the network, and this network generates me an image. Here you see the process of transforming the output vector into the image in some sort of explicit form. So that's what I have told you in the lecture number 1, that we can reinterpret images as the vectors of some higher dimensional space, and I am reiterating that every few minutes, I guess, but here is that's once again in an explicit form. So this generative network should be able, getting some random input, generate me something at the output. but what's the point? So what that? Here we have a space of our inputs. I choose a point in from this space, and my network generates me something. That something lives in a space of all images. I may want to make my network generate something specific. For example, I want an image of a cat. So I don't want some random noise. I don't want, I don't know, some table or a phone or a dog. I want a cat. So whatever input I give to my neural network, I should be able to get some sort of cat. All these images of cats, we can consider them in that highly dimensional space of all possible images as distributed somehow. So we have some distribution function that describes me the probability of a random taken image from that space to be an image of a cat. If I use this generative network, I put some input, I get some output, some image in this space of images. I can compare that whatever I have there, that distribution of results of this network, with the distribution of photos of real cats, and basically make a decision whether this network performs its work as it should or it does not. How is this done? This is done in a, I would say, pretty creative way. Instead of one neural network, we train two neural networks. One is basically generator, so that's our generative network that we need. The other one is the discriminative network. This network takes an image generated by the generator and tells me whether it was generated by generator or this was some image from some ground truth. So I have photos of real cats, I have a bunch of them, and I have something that was generated by my generative neural network. If I put photo of a real cat into discriminative network, I expect it tells me this is a real cat. If I put something generated by the generator, I expect it to say me that was generated. So that are results I am expecting from my discriminative neural network. What else? Now I will train these two neural networks together. So first I'll train a little bit this discriminative neural network, so it starts to discriminate between photos of real cats and some stuff generated by generator. After I have trained it for a little bit, I can use results of this discrimination, like the probability of that thing to be a cat, or a real cat, or cat generated. I can use it as a loss function to assess quality of my generator, and even more to use it for backpropagation and train it to generate more realistic photos of cats. So, not going into all of these details, I should tell you that this is basically a tug of war between two neural networks. So one neural network is a discriminator that is trying to get better and to always guess correctly that this cat was a real taken photo and that cat was generated by my generator. And the other party in that tug of war is basically my generator, that whenever discriminator gets better, it's trying to get even more better and to generate such an image that cannot be distinguished from the real data. And it turns out that all this process, it converges, and at the end of the day we get two well-trained neural networks, and one of them is capable of generating pretty naturally looking pictures. So here are some mathematical details, I'm not going in, so just for you. So we are a little bit training for some steps discriminator. So here we have trained it, so we perform some gradient steps. After this train, we just freeze it and we train our generator using results from the discriminator as a part of its loss function. After we have trained it for a while, we return back to our discriminator, so on and so forth. One more architecture to consider, so recurrent neural networks. So up to this point, all the neural networks we have considered, they were just taking some inputs and producing some outputs, and had, let's say, no memory of whatever they are performing. So if you put through a neural network a photo of a cat, then a photo of a dog, they will make the same. It will be the same result as if you put first photo of a dog, then a photo of a cat. So nothing changes. Here we have one more key idea. Why don't we save some additional data in the neural network or somewhere else, so that the output will depend not only on the current input, but on the previous inputs as well. Why do we want that? Of course, we may want to analyze some time series or some forms of information like text or something like that, where the preceding makes sense. So we are inputting some words from the text, and of course it has a rather big meaning whether we put them in a certain order and not just random. So in this case, we have this new idea implemented in the recurrent neural network. So its sole purpose is to handle sequential data. That may be text, that may be speech, that may be some time series, that may be sound, that may be whatever you think. And it's trying to preserve the context across time steps. So whenever I'm adding new information, it is trying not only process that new information, but take into account the previous information it has seen. The key principle is that output at the time t depends on current input and previous hidden state. So here you have an image that shows you this sort of hidden state. So here we have some layers of the neural network, and you see that when we have some input coming in, so here it is, so we have some input coming in, this input is concatenated with some sort of internal data that we have stored. Then we generate a result that is shown to the user, and we generate some update to that internal data. So if this data was known at the timestamp e, here we will have some data at timestamp e plus 1. And these will be used on the next step when we get some new input, and we can use this updated value to preserve the context of whatever is happening there. Here is another form. This is the same network, just presented in a different form. When we are putting this data one by one, timestamp t minus 1, t plus 1, and all the times we are generating some output and some hidden value that is passed to the next timestamp. This hidden state acts as a short-term memory, so there is some sort of memory to the neural network. The same weights are reused at every time step. So that's a sort of temporal parameter sharing. We had spatial parameter sharing, now we have temporal parameter sharing. It can learn dependencies across time, so like predict next word or find some pattern. So this output may be a prediction of the next word and so on. Of course, it has some limitations, so we have some problems with RNNs like vanishing or exploding gradients in case of large sequences. Maybe the problem, and today they are mostly replaced by transformers, but still good enough to illustrate some temporal recurrence and state propagation. Where can we use them? So in some simple cases we can use them for text generation, speech recognition, signal time series forecasting, or some music or handwritten generation. Here is one more example. So this is a simple RNN. Here we have some RNN layer. It is already present in the PyTorch, and I'm just using that one layer. And here I'm trying to make it predict this sort of sequence, so ABC, ABC, ABC. Whatever I do, I train it on the sequence, and the interesting part is that after I have trained, here I'm trying to perform a prediction. So here I have some sort of input char. So I start with input character A. I put that input character and the hidden state into my model. So here you see how I do that. So I'm just calling model with two parameters, so input and hidden state. I get output, that is predicted symbol, and a new hidden state. And I can print out that predicted symbols. I can print out them, and I can look whether the prediction looks like whatever I expect. And here on the next iteration of the cycle, I take the predicted symbol as a new input and ask for the next prediction, next, and so on. So whatever I get is this thing like BCA, BCA, BCAB. If you add the initial A I have started with, we'll once again get ABC, 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 so the sequence was perfectly predicted. Well, it's not strange because I have trained it on the pretty same sequence, and sequence is really not complicated, just 3 letters, but that illustrates the idea and how do we handle that information. So so please see that here on the forward we get hidden state, we get X, so we have 2 inputs, and we generate 2 outputs that are returned by the return function. And we have a complete RNN layer inside of the PyTorch, but of course you can use some different layers, so whatever. And here is this model just plotted in form of this graph. So here you see RNN layer, here you see some input getting in, and hidden state, and when we get that, I guess this is a hidden state, that's our input, and here we have a new hidden state, and here we have our output. One more architecture to consider is LSTM, so long short-term memory. We have just seen the RNN neural networks, and we know that they have certain problems. So you cannot train them on a really long sequences because we have problems with gradients, so on and so forth. So the idea was to change them somehow to solve these problems. So to overcome somehow the vanishing gradient problem of standard RNNs by introducing some memory control. And the key idea was to add a cell state that carries long-term information controlled by certain gates. So here is an LSTM unit. Here you see this in some sort of unwrapped form. You should remember that in practice you only have something like this one block. So here is just one block you have. You are just passing some input in here. You are passing your hidden state, and at the end of the day you get updated your hidden state, and these updates will be then reintroduced into the same unit with a new input data, and here you get some sort of prediction or whatever. Okay, what do we have here so interesting? So the upper line, that's a CT. This is internal memory of the cell. You see that each LSTM unit it decides what to remember with the input gate, what to forget with the forget gate, and what to output with the output gate. And let's consider quite briefly the formulae and see what happens in here. So the upper line, so this one, that's the memory of the cell. This is performed as you might see in here. This is a forget gate times whatever we had on the previous iteration, so your old memory multiplied by certain parameter that tells you how much do you want to forget that old data, plus some input gate times the candidate state. So here you calculate some sort of candidate state basing only on current information, and you add it with some weight I that tells you how much you should balance between the old information and the new candidate state. So here are some more formulae. You can see then that forget gate is basically some layer. So here it is, you have inside of this layer, you have some matrix multiplied by all of that, so some weights, and at the end of the day you generate one number that is multiplied by this CT that we have here. Then we have candidate state calculated like this. This is the candidate state, I guess. Here it is multiplied by IT. Here it is. They are multiplied and they are added to the old data that was multiplied by the forget state. And now we can use this sort of result and our input to get some sort of outputs HT. So here we have our outputs, so it is performed like with this formula. So here we have information from the candidate state that gets through the tangent, and it is multiplied by some number that we get from the input, so that's from the input we had, and this goes to the HT. So here it is. So that's our output. Okay, so it looks a little bit complicated, but the general idea is that inside of this cell we calculate few numbers, some weights for how much do we want to forget our previous information and how much do we want to incorporate our current information. Our current information is calculated from our current input data, so that's a new so-called candidate state. We collect that together and we get some new hidden state, and then we use this hidden state together with our input data, so to generate our current output. So our prediction, for example, prediction of the next symbol of what we will have inputted in the next time iteration. Okay, now one of the most probably popular architectures right now, the architecture of the transformer. So we have seen RNNs and LSTMs. They both perform more or less, but now we have some really large, really deep neural networks that are called transformers. So the idea of the transformer is to do something with all that LSTMs and RNNs, because they have one fundamental flaw. If you train them, you should input all the symbols one by one. So you cannot train them simultaneously of a number of symbols. Transformer neural network solves this problem by basically allowing you to train your neural network on a number of input symbols or tokens simultaneously, and thus you can get deeper and larger neural networks and get much better results. So if you have seen some sort of chatbots like ChatGPT or whatever we have there, so they are based on this sort of architecture, and you might probably guess that it is really looks like really a breakthrough, because previously we had nothing that looks so intelligent and generates such well-crafted texts. So here is an example of that transformer. So it was introduced in the article. So here you have a link. It is called "Attention is all what you need." That replaces recurrent and convolutional layers with self-attention mechanisms. Maybe I'll tell you a few words about that. And that allows you to process sequences in parallel, not step by step, enabling efficient training and long-range dependency modeling. Here you have this sort of transformer model. So on this part you see the overall transformer, how that looks like. Here are some building blocks that are the most interesting, and probably the most interesting block is this sort of multi-head attention. So what is this multi-head attention and why it changed everything? So while it changed everything. So here we see a few blocks with multi-head attentions. So here is one, 2, 3. So here all they are. So one is masked multi-head attention. I'll say a few words what that. All the rest blocks, they are not so interesting. It's just simple feed-forward networks. Well, not simple, but they do not contain such a breakthrough ideas, so I don't see any reason to consider them in details. Moreover, in cases like ChatGPT, that's a commercial secret, so we can't even know what's in there. But some things about multi-head attention, I guess we need to get through. So okay, what about this network and how does it operate? So the overall structure contains of encoder and decoder. So here you see on the left part of the encoder, and this is a part of the decoder. So encoder, it takes input tokens and it embeds into vector, it transforms into vectors, and positional encoding is added. Each encoder layer, that's a multi-head self-attention. Each token attends to all other in the sequence. I'll tell a few words in a bit how that works. Then a feed-forward network applied independently to each position, and outputs are contextualized representations for every token. So here you see that everything is performed simultaneously, so you can work with many tokens if you have many, let's say, processors or GPUs or whatever. So decoder has a similar layered structure, but includes an additional encoder-decoder attention block, so where you collect information from encoder and decoder, and each layer you consider. So you have masked self-attention, encoder-decoder attention, and feed-forward network for further transformation. Okay, so what about the attention? First, consider this part. What do we have here? So we have inputs. Inputs is some sort of text. You can split the text into tokens. Tokens may be words, maybe some larger chunks, whatever you have. Probably words that you will have. In RNNs and LSTMs, we were just simply sending them one by one into the neural network. Now we want to send them all simultaneously. But if we do that, we will probably use the information on their positions. So here is the trick how the positions are encoded into the input that gets further into our neural network. So here I have some tokens. These I will transform these tokens into some sort of vectors. It doesn't really matter how I do that for the sake of general idea. So I have some tokens. These are some words. I know cat is cute. So I have one token, I have another token, I have one more token. They all are transformed in some sort of vectors. So I have a vector, I know 1.5, 0.3, some data. Here I have another vector that contains, I don't know, 2, 3.9, so on. Here I have another vector, 1, and so something more, and so on. Now, I don't want to lose the information on the order of words in the sentence. So you probably guessed that just juggling words around won't do anything good, because you will get from the sentence with one meaning, you will get something pretty different. So basically in here you see these squiggly lines. They represent something like signs. So I have some sine wave, I have some larger sine wave, I have even larger sine wave. So for the position number 1, I will add to here a vector. So here is the position number 1. So these are ones. I can calculate the values of these sine curves. I get some numbers in here, and I put all these numbers in this new vector, and I add it to the embedding vector that I had. So this plus sine tells me that I am adding this positional encoding to the representation with embedding. So here is 1 on the x-axis, and here I get some numbers, I don't know, so let it be 0.9, 0.75, 0.5, I don't know, some random numbers that we get here. So here is that 0.5, so here let it be 0.9, and this one let it be 0.75. So so that's some random numbers, I mean not random but calculated from these signs, and I collect them into a vector. Of course I may have more of them depending on the number of the dimensions of the space I have embedded these words in, and I do so with each of these words. But this one has position 1, this will have position 2, so I will take number 2, and I will get some different numbers in here. So this will be some like minus 0.5, and this will be some plus 0.9, and this will be, I don't know, 0.75, and so on. So I guess you get the idea. I'm adding everything this, and now I have in here, I already have information on the positions, and I have information on the tokens I have used. Good. We have embedded our data. If we are creating a network for, let's say, some sort of translations, we do the same for the expected outputs. So I have some phrase in here in English, so the cat is cute, and I have some expected translation, I don't know, in Japanese, like Neko ga kawaii desu, and we have that we need to somehow run that through the transformer and train it, and we have many such phrases. So good, we have encoded information, let it be. Now it gets to the multi-head attention. What is multi-head attention? Multi-head attention tells us about connection of the words within the phrase. So how the words are connected, and how strongly are they connected, and what should we do to get to incorporate that connection into our training. Basically, we are generating 3 vectors that are called key, query, and value. And here is the formula that shows us what do we do with these sort of values. So if we think of them, one is something like vector, the other is like covector, and if we multiply them, we may be able to calculate how much do these 2 words relate one to another. So how strong is the relation? It's something like, I don't know, I took pizza from the oven and it was delicious. And here, if we think about the word it, this word it may, of course we know it corresponds to pizza, but it could correspond to oven. But we know that ovens, they can be delicious. So probably if we consider that for a while and we calculate all these values, we should be able to get numbers much higher to the correspondence between it and pizza than between it and oven, or it and delicious, or whatever. So they are basically vectors in multi-dimensional space, and by multiplying 2 of them we get some value that tells us how much are they related, and this value is basically the result that we want to propagate further, multiplied by the strength of their relation. So that's the attention layer. We can have masked attention layer, so this is M. It sets some scores to effectively to minus infinity, just eliminating some of the connections. You can find it only in the output layer, and it is used to somehow prevent cheating on the of the neural network during training, and to not let it create connections between tokens that are in the future. So like when it generates some text, it has generated say 5 tokens. The 6th token should be connected to that 5 tokens and generated on the base of that 5 tokens it already gave us, but not on the tokens that we expect from it in the future, because it cannot predict future. It just should be based on the current state. So this is the only place where you see that masked multi-head attention. So here it is. So whatever we do, now we have that sort of attention. Multi-head just means that we are stacking few of these layers. So here you see that layer with 3 inputs like query, key and value. These matmul and scale and so on are performing that operations I showed you, so that scalar multiplication and so on. And here they are stacked together so that you may so that the neural network may learn different connections between the words in using like different contexts. So you may have a few different layers stacked, and thus you get so-called multi-head attention. I'm not sure how many of them are used, so it may be maybe some number. Good. And using this multi-head attention, we get all that values v, and we put it through the feed-forward networks, and at the end of the day we get some result that we expect. Okay, so that's it has some quite advantages. So this neural network is highly parallelizable, so that makes training much faster. It captures long distance dependencies effectively, and it scales well. So that was a nice foundation for such models that are known today as GPT, BERT, T5 and other language models. So this is a good network to perform some sort of translation or generation of text. Okay, now let's consider some more neural networks, and this time I want to consider so-called stable diffusion. Stable diffusion is not one but few neural networks that are used and even trained jointly. So okay, so first of all, what does it do? So you can, with stable diffusion, you can generate some images by giving a text prompt. We have already seen some ideas for generations with generative adversarial networks, but now we want to incorporate some new information into that. How it's performed? We have some separate neural networks for a network, for example, for text encoding. So it may be, let's say, clip text. So you use you input text and you get some number of tokens or embedding vectors in a higher dimensional space. So in this case, like 768 dimensions. Then we have a UNet architecture that we have already seen, and scheduler to gradually progress diffuse information. I will show the process of training just in a moment. So we have text embeddings and multidimensional array made up of noise, and we try to make our neural network to generate something. And we have autoencoder decoder that is used just to make everything, let's say, quicker. So instead of generating raw image, we generate something in the latent space that is later increased by the decoder from the autoencoder. Here I have once again some article that explains everything, but let's get into the details a little bit. So training of the diffusion model can be divided into two parts. So we have a forward diffusion process, so we add noise to the image, and we have reverse diffusion process that removes noise from the image. So here are these images. So here we have a forward diffusion process. We have a nice image, but we add and add and add some sort of noise. And here we have some denoising when we put some noisy, something quite noisy, and we want to get some clear picture out of that. So image plus noise is given to neural network, and expected result is predict correct noise. So let's look at that. In each epoch, we take some random timestamp for each training sample. We apply Gaussian noise corresponding to that timestamp to each image, and we convert timestamps into the embeddings. So the neural network will know the timestamp and the noisy image that we have. So here are some examples. Here we have epoch 1, we have some noisy images. These may be different noisy images. We have different random timestamps depending on that timestamps. So the larger the timestamp, the larger the noise. But here for the epoch, they are chosen pretty randomly. We have some embeddings for that timestamps, and we use that together with the noisy images. We feed them into the UNet architecture, and we demand to get something out of there. What do we demand? What does it look like? So for each training step, we randomly select this timestamp, we encode it. Now we take an image, we add some noise to that image that depends on the timestamp. You can see these sort of t's in here. So alpha t is result of multiplication of all the alphas before this timestamp. So we have some randomly chosen that alphas. So on. Now we train our UNet architecture to do what? We give it this noisy image and we give it a timestamp embedding. As a result, we expect prediction which noise was added to the image. And as a loss function, we of course can make a difference between the true noise and try to calculate how good this noise was predicted. Of course, if we have predicted noise, we can subtract it from the noisy image and try to get back our initial crispy nice image. Here is one more example. So here is a sample of Gaussian noise. So here we have it. Here we iteratively denoise the image. So we can take basically something very noisy. So we have trained our neural network. It can take noisy image, timestamp, and predict noise. We can subtract that, get better image. Okay. After training, what can we do? So interesting. We can take some large timestamp and absolute noise. So we don't even take any image, we just take a random Gaussian noise. We put that noise with the timestamp into our neural network. We get some prediction. We subtract that prediction from the initial noise. And whatever we have, we put back into our neural network, ask it to calculate once more noise, but we change the timestamp. So if that was a timestamp 1000, we say let's do that timestamp 999. We do so many times, and at the end of the day, our neural network is able to generate an image from basically the pure noise. So we had clear images, we made them noisy, and we asked our neural network to get that noise out of the image. Now, after the training, we are getting a pure noise into the neural network, and we expect that it may get some image out of there for us. That's a pretty similar thing that we have done when we considered generative adversarial networks. So we put there some noise, and we generated an image, for example, an image of a cat. Here we put some noise, we get some image. The difference is that we have different approaches to training. For the generative adversarial network, we trained two different networks, generator and discriminator. Here we have just one neural network, but we perform this sort of step-by-step procedure by adding noises to images and adding these timestamps. The diffusing or sampling process iteratively feeds a full-sized image to the UNet to get the final result. This makes the pure diffusion model extremely slow when the number of total diffusing steps t and the image size are large. Well, that's pretty reasonable. So you have many images are large, and you need many steps, like thousands or 10,000, so that's no good. So the original name of Stable Diffusion is latent diffusion model. So here comes the second idea. So let me generate not just image from that with that sort of diffusion, but let me generate some something in the latent space that can be later transformed into the image by the part of the autoencoder, so by the decoding part of the autoencoder. and the name points out, the diffusion process happens in the latent space. That is what makes it faster and than a pure diffusion model. After encoding the images into latent data, the forward and reverse diffusion processes will be done in the latent space. So forward diffusion process adds noise to the latent data, reverse diffusion process removes noise from the latent data. So here is an example. I have image, I have encoder, here I have latent data, and decoder I expect to get image back. So that's pretty, that's just an autoencoder. Here we have diffusion process in the latent space. So latent space is much smaller. So if I operate with images like 1000 times 1000 pixels, latent space maybe, I don't know, 100 times 100, well, something small, let's put it this way. And here we have the denoising U-Net that performs all the work. And the true power of the stable diffusion model is that it can generate images from text prompts. So that is done by modifying the inner diffusion model to accept some conditional inputs. So here we have an example. Here we have some conditioning, so some text like Paris in Milky Way. We have that neural networks, that transforms text into embedding. I have said that to you previously. Here we have text embedding. Here we have some random latent noise. Here we have some timestamp embedding. We get everything that into the diffusion model. In this case, that's a latent diffusion model, so we generate something in the latent space, and now we use the decoder to get our final image. So that's how it looks like. Here is example of what we are doing a little bit more precisely. So the inner diffusion model is turned into a conditional image generator by augmenting its denoising U-Net with the cross-attention mechanism. And we have seen that cross-attention mechanism in the transformer just a few moments ago. So the switch below, so that's this one. So here we have it. Is used to control between different types of conditioning inputs. So for text inputs, they are first converted into embeddings vectors using a language model like BERT or CLIP, and then they are mapped into the U-Net via the multi-head attention layer. So you can directly put them into the multi-head attention layer. For other spatially aligned inputs like semantic maps, images, in-panning, whatever, the conditioning can be done using concatenation. So you can just concatenate that latent space representation with some additional data. So here are some variances, what you can do, what you can get. Here is once more the architecture shown again. So here we have different embeddings, some random latent noise, timestamp, and some conditioning embedding, probably generated from some text prompt, but maybe something different. And this is reverse diffusion. It's not many neural networks, this is one neural network, but just repeated few times. So as with the RNNs or with LSTMs, you can think of getting some outputs and use and reuse these outputs at the inputs for the next step, and repeating these for some number of times, some t times, we get some result we will be probably satisfied with. We put that through the decoder of the autoencoder and we get some nice image. Here is the same process shown once again with images. So here we have forward diffusion process, we are just adding some noise. Here is some inverse diffusion process when we repeat t times this sort of denoising, and we get some nice image at the end. And here are the same schemes shown once again just in one slide. So here you have forward and backward diffusion processes, and here you see like when you use image, you use encoder, you get latent space representation, you get some noise, and here is a noisy representation in the latent space. And here is decoding. When you have noisy representation, you have timestamp embedding, and if you have some conditioning information like embedding of the text that describes what you want to have in that neural network. and you repeat t times. You take the same network and you just put this you put all these into that network. You get some prediction for the noise, you subtract that noise, put it once again and again and again, and at the end of the day you get latent space representation that can be put through the decoder and you get the image. So that's it. And now to the last architecture that we have. This is a idea of the neural fields. The term of neural field was popularized by C, I hope I read his name correctly, and describes a neural network that parameterizes a signal. What have we started with? That neural network is a function. So basically, why don't we use neural network in some context where we need a function? So why not? It will calculate something for us. So the signal that we are trying to parameterize usually is a single 3D scene or object, but that's not mandatory. You can also use neural fields to represent any type of signals, discrete or continuous, such as audio or images. Their most popular use in computer graphics applications such as image synthesis or 3D reconstruction, and in most neural field variations, fully connected neural networks encode objects or scenes properties. So importantly, one network needs to be trained to encode a single scene. So it's like you are making your network heavily overfit. So you take a single scene and you do everything for this neural network to remember that scene and to capture all nooks and crannies of that scene that you have there. So that's pretty crucial. So that's an overfit that we can use for something. The typical progress of computing neural fields can be formulated as follows. So we sample coordinates of a scene, we feed them to a neural network to produce field quantities. So it generates for us some sort of field in space. So it can be some vector field, some tensor field, it can be some scalar field, so whatever we need. I will show one example. Sample the field quantities from the desired reconstruction domain of the problem. We map the reconstruction back to the sensor domain, and we calculate the reconstruction error and optimize neural network. Let's get through an example. So here we have a scene. So I have some object, and this is some object in 3D. What can I do with this object? I can observe it. So I can look at this object, I can look at certain point in 3D. A scene is represented as follows. I take any point from a scene and I take some direction from which I look at that point. And I calculate from that point some sort of color that I will see and some optical density of that point. This color and density will define for me a field. So I can take any point in 3D, and with this point I have color and optical density connected with this point. So basically I can describe this as sort of field in 3D. And now I will train some neural network. I will make it sort of heavily overfit, but I'll force it to remember this scene up to each point. So why we use neural field to represent objects? So neural fields are very efficient and compact 3D representations of objects or scenes. In contrast to voxels or meshes, they are differentiable and continuous, so we can use some sort of operations on them. They can also have arbitrary dimensions and resolutions, and they are domain agnostic, so do not depend on the input of each task. Here is an example of that neural field, like NeRF example, when we are representing that sort of scene. So here we have some world coordinates. That's a mathematical representation, and here we have some sort of meaning that we can that has that sort of quantity. So world coordinate x, and this is a 3D point of an object and direction of view at this point. So 5 numbers in total, so 2 angles and 1 3D point. Field quantities. So we have some field in this space. This is RGB color and the density sigma. So these are just 4 real numbers. So neural network will give us 4 real numbers. Field phi So mathematicians call that phi, they call it a field, and that field prescribes to each point in space some numbers. We call that a neural network. So we train it. That's often some sort of multi-layer perceptron. It takes everything, all the data inside, and gives us 4 real numbers. Now, sensor coordinates have nothing to do with the neural network itself, but we need it for training. In this case, that's camera positioning and pixel coordinates. So we have positioned camera, we had made some photo, and we had sort of image. And measurements. So what can be a measurement? So if I made a photo with the camera, I can look at certain pixel and I can ask what is the color of this pixel, so RGB. So here we have some sort of sensor omega that's a procedure of taking a picture, and the forward mapping that we will use in our process of training, it's called volume rendering. So the general idea, I have a neural network that represents me all the points with these 4 numbers. So I give it a point, I give it some sort of direction of view, and that gives me some sort of density and color. From that density and color, I can somehow calculate the image that I would have taken if I looked from that direction to that point and had a camera. So if I have a camera, I make a shoot, I get some image, I can look at pixels in that image, and what kind of pixels would I have are basically defined with this sort of forward mapping. And of course, if that happens, I will be able to compare my images generated with neural network and the one I have taken with my camera. So here is the example of volume rendering. So how do I do that? So I'm just sort of integrating all the points along the lines of view. So I have some point of interest in 3D, let's say this one. I have a direction of from which I am looking at this point, let's say this one, and I can take I can sample these points along the path. So I just ask neural network what is the color and what is the sigma for let's say this point, and for this point, and for this point, and for this point, and I can integrate them along the path. And at the end of the day, I will calculate some sort of color and say, well, if I take a picture from this point of view, I will have this pixel will have this sort of color. Here are some some formulae regarding that volume rendering, probably the most complicated part. So light travels through a volume that both emits and absorbs light, and each point may emit or absorb light. Most cases you will have no emission, and each point along the ray may emit light with intensity Ct or may absorb or scatter light according to its density sigma t. So we predict that sigma t. The camera receives only the portion of light that is not absorbed before reaching it. Here we have volume rendering integral. So here you see this sigma, you see this c, and here is a the array is parameterized in this way, so it's just a straight line defined by vector, direction vector, and some point where we put our camera, the origin and direction, origin O and direction D. And here is how the t is defined. So t is sort of transmission, that's a fraction of light that survives absorption from t near to t. So here we have all the formulae. I'm not getting into much of the details. I'll better show you some nice pictures. So here is how the rendering is performed. So I have a scene, I have trained my neural network. So when I ask something about the point, let's say this point here, I ask, what do you think about it, neural network? I give it coordinates of this point, and I give it and I give it some angle of view. So here are theta and phi for these angles. It generates me 4 numbers like RGB and some sigma. So here I have for this point some RGB and some sigma. And when I perform volume rendering, here I have these sigmas, how they change along that line of view. So along this line, I am constantly requesting from the neural network what what it thinks about each of these points along that line. I integrate all of that with the formulae I showed previously, and at the end of the day I get some sort of color. So you see this rectangle, it has some color, and that is the color I was able to get with integration. And of course I have some sort of ground truth, because this direction was not chosen randomly, but I have some sort of ground truth. So I have this object photographed and I have some photo of this object, so I know what kind of pixels should be there, and I can compare them and calculate the rendering loss. And here you can see how that's performed in practice. So we have some 3D object. I can make photos from different sides of this object, and that will be basically my training set that I can use to make my neural network represent this object correctly. And at the end of the day I will get my neural network trained. And what will this neural network be capable to do for me? So first of all, I have some limited number of photos, but my neural network will be able to generate me some views in between. So whatever view I choose, it will probably be able to generate that view and give me some nice image from different sides of the object. And of course I can use some additional information generated by neural network, like all that sigmas, to calculate something interesting. And that's basically the general idea of the neural field. It's using neural network as a function. So we have returned, in some sense, we have returned to where we had began. So we began with neural networks as functions, but we used some effort to transform our problems into problems that involve finding the function. Now we have neural network and we use it just directly as the function without any other meanings, and that's pretty interesting, I guess. So with that being said, I guess now we conclude our second lecture on the architecture of different neural networks. Of course, there are many more neural networks and many more nice ideas that people use when building all that stuff. But I hope that I have covered more or less some most fundamental ideas, or the most let's say widely used ideas, and you will probably meet them here and there if you work with neural networks, if you construct your own neural networks, and maybe some of these ideas will help you to make your neural networks better. So with that being said, we wait for the third lecture.